Hi, everyone. So yeah, that was a very short intro. Uh, you're organizing. But yeah, thanks for coming today. Thanks, Sasha, for hosting. We used to work together, what, 6, 7 years ago, deploying Airflow when it was new. And he always believed that data should stay with the data team and they should define the KPIs. I can tell you that never changed. So I'm happy to see that now again. So yeah, I'm going to talk about Cognee. That's a product I'm building. And yeah, we are working in the LLM space. We are working on AI memory, and I'm going to tell you what that is about. So first of all, who am I and what's the story? So I'm Vasilij, originally from Montenegro, grew up in Serbia. My background's in business, engineering. I'm also studying psychology. I worked in the data field for around 10 years, started as a data analyst where Sasha was senior, I was junior, and moved to actually Omio, where I worked as a project manager, worked as a data engineer in a few places, worked as a team lead at TaxFix at the time when they were scaling up. So yeah, for the last 3 years, been working as a consultant, and now I have my own startup. I'm working with Boris. He's my co-founder. His background is purely in engineering, back end, front end, full stack, and we are building this together. So let's talk about the problem. So since the LLMs appeared, we've been trying to personalize them. So you tell the LLM or ChatGPT, hey, you are now an engineer, or you might be a programmer. We give it some special instructions. We copy paste the context or documents or information we want a better answer to. And we use one of these many prompt engineering techniques. So we can chain some set of prompts together. We can ask it to, in parallel, analyze and do things. We ask it to automatically reason, use LangChain, use Llama Index, all of these frameworks that let us really tie in all of these elements together. But none of that really gets us very far, right? So we all see that this personalization problem is somewhat still there. And the reason is that, yeah, you can fine tune an LLM, you can improve it to a degree, but that again requires GPUs, requires power, requires a lot of extra work. So they're not really our, sidekick and assistant, although everyone's making an assistant now. They are at best this probabilistic set of tokens we are predicting at any given point. So what people try doing to fix that is they tried actually building RAGs. How many of you know what RAGs are here? Okay, not too many. So RAG stands for Retrieval Augmented Generation. What people do is that they use an LLM, and instead of actually focusing on just giving it some context and copy pasting stuff, they put data in a specific set of data sets in a vector database. So the vector database allows us to store the data in the embeddings that we can then retrieve together with the query and pass it on to the LLM to get a better response. So it's like copy pasting the context just on a bigger scale. And why vector databases are good is because they let you actually do similarity search. So if you upload, like, let's say 50 documents, and one is about the apples, once you search information about the apples, the vector database will give you the apple-related information that you would pass to the LLM. But this doesn't really get you far again. So let's see why. So if you search for I like Apple, what do you think you would get as an answer here out of these three possibilities in the vector database? Okay, he knows, he saw the preview. Sorry? Actually, one you won't get because semantically it maybe has an I, but nothing else is similar, but you'll get number 3. So why is this a problem? Is because LLMs effectively have no semantic understanding of what you mean or any logic to themselves. So when you want apples, you might not get apples. And simply the answer that you're going to get is with very high likelihood score going to be I don't like apples because it has it has like, and it has apple, but it won't understand the don't part. So what that means is that when you ask LLMs for something and you load the data to vector store, you will not be able to get the accurate information often enough, and you'll get to what they call hallucinations, but also you will just get to inaccurate result. So that's where, well, we come in, of course. And what we're trying to do is we're trying to create a semantic representation of the data. And we are trying to actually decompose the data and pre-process it. So when we give it back to the LLM, it has this set of multi-layer graph networks that contain propositions. So you can see some content that's being decomposed to the right. I should have maybe magnified that, but let's go back slowly on to what we are trying to actually do. So first two concepts that I'm going to introduce is, one is the multi-layer network, and the second one is the propositions. A proposition is the smallest amount of text that you can summarize that represents a fact. So what we do is we take text, we summarize it into these factual statements. And then these factual statements, what we do with them is we actually store them in multi-layer networks. Multi-layer networks are frameworks for investigating the mental lexicon. This is, in psycholinguistics, it's a complex cognitive system that represents some information. So on a picture, in psycholinguistics, they would define it something like this. You could decompose a word into syllables, graphemes, and then create connections between each of them across many layers. We do this, but just with one level up with these basic sentences. And we split them across the layers that we let the LLM define based on the text. And then we interconnect all of these. So what that lets us do is to have different layers of meaning. For example, if you take some type of scientific article, we could split it based on the author's abstract method, any other type of or element in the title, for example. And each of these would be layers. And within each of them would be a proposition such as the result is, or the author is, or any other. And all of these layers would be interconnected, and all of these propositions would be interconnected in a graph of nodes and edges that would let us have these logical connections and relationships defined. So we can actually use and see the data and give it to the LLM with already understood connections between them. So that's the assumption. So this is very abstract so far. So let's see how that actually works. So 10 days ago, it feels like 10 years ago. 10 days ago, we released the library. And the library is just a simple Python tool that lets you load any type of data. So we load some data folder with some information to our metadata store. We normalize it here, get the IDs, do all the data engineering stuff. So we can actually reuse it later on. And here you can see that, yeah, in the DuckDB, we loaded this document. We have a unique ID for it. And then it's normalized. We can use data contracting on top. So all of the stuff that usually these AI startups need help with because they don't have the data engineering experience. And then in the next step, what we do is we actually call this Cognee.ai function. So this Cognee.ai function is what is going to actually decompose all of this data into these sets of propositions and graphs. And what we do here is we use LLMs, and we use LLM function calling. So we give the data to the LLM, and we say, hey, this is the expected output. So in this case, we use classifiers to actually categorize the data. So you can see that this document is categorized as laws, regulations, and legal case document. And then we see that for this document, we can create some layer of graphs, some layers, some summaries also. So all of these we plot in a graph database because it allows us to really easily define these sets of nodes and edges that represent the connections and the logical elements. So how that looks like is something like this. So this is a document node, and the document would contain the layers and the labels, sorry. And then it would contain summaries. And each of these propositions would be a simple individual dot that's connected to other dots based on the meaning. And then now imagine this times 1,000 or 10,000. And all of these nodes, again, interconnect across different documents. So if you are, let's say, Adam Smith, and you published a book on economics or two, if you have each of these, each of these as one of the nodes. You would have Adam Smith as this one of these dots interconnected across. So when you search for Adam Smith, you get all the books he wrote, and you're able to actually navigate these graphs easily. So this is the assumption, and yeah, that's that. The last piece, and this is how we actually do the search, is that what we do in the background is we also use the vector data stores, but we use them to store these propositions. So each of these is a small proposition that the LLM created. We store them in their different namespaces. We go and search for them when we search for something. But then what we retrieve is also all the information from the graph about their relationships and who belongs to whom or who wrote what, and all of that stuff you saw there in the previous slide. And then effectively, we combine all of that, and we also implement other types of searches, filters on categories, on labels, on summaries, and let people actually define their own data model and define their own search type. So we could pass this to the LLM and have a better answer. So yeah, that's what Cognee does. So it's pretty fresh, buggy, but works. So yeah, we hope to continue improving it and work with a few design partners to have this running in production in a few places. And yeah, we utilize, as I said, the graph databases, relational stores, and vector data stores to kind of combine and create an engine on top. Next step is to actually have DSPY, which is a framework from Stanford University, to let us actually go back and optimize and have reverse loops. So after, let's say, bad result or a good result, we can reinforce certain types of connections and make them better. And yeah, a lot of other things on the roadmap too. So yeah, if you like it, give us a star on GitHub, because, well, we might be fundraising soon and investors like GitHub stars for some reason. So yeah, that's all. And yeah, happy to answer any questions.
Any question from the audience?
Great presentation. Where do you fit Cognee in a RAG application architecture? Like there's the vector database, there is a retriever. Do you put it above the retriever, or does it integrate into the vector database?
It's besides vector database, so you can see it as another service you would call in between, and then effectively just as an add-on, so to enrich the response. Okay. So in the flow, you can go to the vector store first. Then when you get the context, you can still go to Cognee, get some more context, pass it to the LLM.
So it's not like a layer, pass-through layer. Yeah. So it's like on the side.
On the side. We don't want to make it pass-through layer because it's harder for people to integrate like this. They can use it as a support tool.
Okay. Anyone else?
Hi, since you have an investor call coming up, maybe I can ask something they would ask. How are you guys planning to monetize this solution?
So yeah, that's a question I've been asked already, so I can answer. So the thing with this type of tooling, and compared to any type of tooling you're going to see tonight, is that effectively the market is not there yet. So in a year or two, the market's going to be there. That's what the competition tells me, the people that have been working in the space. What we are trying to do now is work with design partners. It's mostly AI verticals. So, make your slide, PowerPoint presentations, make this, make that with the AI. And they run into these problems. The traditional industry is not there yet. Germany is definitely not there yet. So I think it's going to take another 2-3 years until this is really in production for a lot of places. And because of this competition to the bottom with the LLM providers and increase in the speed of the outputs and reduction in cost, I think we're going to see a big change in a couple of years, but probably not right now. So yeah, so design partners, we have a lot of calls, a lot of interest to build first products with people, but yeah, full on monetization in probably a year or two.
Okay, thanks. But you're basically gonna say, okay, this is gonna make our chatbot hallucinate less, as an example. Is that how I should see it?
Yeah, among other things, but people don't just use it for chatbots. So there is different use cases. For example, I talked to some American universities last night about building this type of knowledge graph, so to organize courses on universities. So that's what they need it for. Biomed guys need it for biomed data and different other type of use cases. So depends.
Okay, thanks.
Sorry if I just didn't if I didn't get the first time around. But could you say a little bit more about what the nature of the knowledge graph is? Like what's being stored, what's on the nodes, what's on the arcs, like what's actually being modeled in the graph?
Sure. So in the graph, what's being modeled is these propositions, these basic statements of fact. So Vasily holds an apple would be, let's say, a proposition. And then what could be another proposition would be Vasily was going for a meetup tonight. And then let's say a relationship in that context would be before the meetup, Vasily held an apple. So before or after, like temporal one, or even this simple statement like Vasily holds an apple. Vasily is a node, holds is an action, an apple is another node. So yeah, depends exactly on these layers that we define, and we let the LLM choose the layers. So these layers vary. So they can be anything from contextual to talking about authors of an article to any others. So we pretty much leave it to the system to decide on how it really creates these interconnections. But we just tell it like, hey, this is the text, this is the input, give us the connections, give us the semantic understanding, and then it does it. So that's the assumption. It's still probabilistic, but with some type of a grammar set of rules where we define the set of connections and the grammar rules of how they can be interconnected, give it some type of rule system. We can limit the hallucination and again get better outputs.
So are you doing any kind of like syntactic parsing for that? Is it like in the same order of like the universal dependency grammar, that kind of thing, or is it more loose than that? Is it more
currently it's more loose? We are going to work towards more type of a universal grammar.
I have maybe two questions. First would be like, would you say that Cognee mostly takes the data set and creates the node graph out of it? And the second question is like, maybe you've tried this, like to take the Wikipedia, some part of it, and create the graph out of it and compare that's like the Wikipedia graph, what was made by the people, and what's your application is creating. Are they similar or are they better, worse, and in which case maybe you've done this?
Yeah, great question. So yeah, we let the Cognee create the graph. We use the LLMs to decompose. And how do we evaluate is, I think here, that's next on our roadmap is to actually run the evaluations to, see how we can optimize the system and how it compares to the standard models, how it compares to naive RAGs. So there is a lot of work we need to do there yet.